Let's continue now. In this video, I'm going to introduce a very important notion called splitting fields. So what I will do now is let f be some field and let us choose a polynomial f in the polynomial ring over capital F. Let f be a polynomial in capital Fx. We say that, so this is an important definition, we say that f splits completely in an extension f k of f, in an extension field k of f. So this is the terminology. We say that it splits completely in an extension field k of f if f can be written as a product of linear or degree 1 polynomials in the polynomial ring over the bigger field. Linear means degree 1. Linear polynomials means degree 1 polynomials. Okay, so we say that it splits completely, that means all the way up to degree 1. So for example, x squared plus 1, which is a polynomial in rational numbers, does not or let's say splits completely in C, right? Because x squared plus 1 can be written as x plus I times x minus I, where I is in C. It also splits completely, or rather I will write over C, over, so I should just slightly modify this, splits completely over an extension field capital K. If that happens, splits completely over Q adjoint I also, because we don't need all of complex numbers, right, for this splitting, we just need I. On the other hand, it does not split completely over Q, because it's not a product of linear polynomials over Q, it is irreducible and you can't factor it into linear polynomials. It does not even split completely over R also, right? So the base field is extremely important. It is over the base field that splitting completely or not makes sense. On the other hand, x squared minus 1, which is a rational polynomial, splits completely over Q itself, right? Because x squared minus 1 is x plus 1 times x minus 1, right? And this is actually a splitting in the polynomial ring over Q. Here this is the splitting over the polynomial ring over Qi. Okay, so splitting completely means splitting as a product of linear factors. In other words, what we are saying is that f has all the roots in that field. Here x squared plus 1 has 2 roots, but not in Q, only in Qi. You have to go at least to Qi. So it is a field. We say that a polynomial splits over some field if it has all the roots there. We have to be careful about what all the roots means. What we really mean is that it's written as a product of linear polynomials. Okay, so what I want to start with is we want to say that it always there is such a field always. So proposition, let f be any field. Yeah, so actually before I write the proposition, let me do the main case of this as a separate remark. So let's say f is a field and let fx be in capital Fx is an irreducible polynomial. That is irreducible of positive degree. So degree f is positive. Then f is a maximal ideal in Fx. right? This is something that we have seen many times before. If you have the polynomial ring over one variable or a field, the ideal generated by a irreducible polynomial is a maximal ideal. So let K be the field fx modulo f. Then what we want to say is that this is a very simple point, but it's an extremely important point. Then K is a field extension of f K is a field extension of capital F in which fx has a root, namely x bar. Okay, so let me explain this. What is the explanation for this? So the reason, so this might not look like a field extension a priori, but it is in fact a field extension. That is because, remember, f always sits inside fx, right? So there is an injective map from f to fx. And now what we are doing is fx mod the polynomial, the ideal generated by the polynomial f, and that's k. This of course is not injective, not 1 1, right? That is because the polynomial f goes to 0 here, so that's not injective. But the composition, this is a field homomorphism, right? This is a field homomorphism because the first one is a ring homomorphism, the second one is a ring homomorphism, the composition is a ring homomorphism. A field homomorphism is really nothing but a ring homomorphism between two fields. F and K are fields, it's a field homomorphism. And as such, if you call this phi, phi is injective, right? In fact, phi of A is actually A for all A in K, all A in F. In fact, phi of A is equal to A for all A in F, because where does, so if you just trace the maps here, small a goes to small a, right? It goes to itself as a constant, and then this goes to A bar, but I'm going to identify that with A. So we think of F as a subfield of K. Really, to be very precise, F is isomorphic to its image, which is a subfield of K, and we are identifying F with that image. So we can think of F as a subfield of K. So K is a field extension, in other words, right? What is a field extension? It is simply a field containing this field. That's the first statement. It is a field extension of K, F, in which fx has a root. Now what is x bar? Just to be more familiar to you, I'm going to think of the image of x as alpha. So denote x bar by alpha. So then what is f alpha? What is f alpha? F alpha I claim is 0 because f alpha is equal to f of x bar, but then this is same as f of x whole bar, because the map here sends, the second map takes a polynomial and sends it to its residue, which is simply replacing x by x bar, but fx bar is 0. Okay, so this is extremely important. This is a very important observation. Okay, so in some sense there is a God-given procedure to obtain a bigger field where any irreducible polynomial has a root. All you need to do is go modulo that ideal generated by that irreducible polynomial. Because that ideal is a maximal ideal, the quotient ring is in fact a field and the residue of x is a root of the polynomial. So to illustrate this, what we do, let's for example consider x cubed plus 2. Okay, this is irreducible. This is for you can see this in many ways. For example, Eisenstein criterion shows this. So what do? We take k to be q adjoined x cubed plus 2, right? This, by the observation I made earlier, is a field extension because the rational numbers are not really disturbed in k. Only x becomes x bar, but rational numbers under this composition of these maps are unchanged. So this is a field extension, and x bar here satisfies, right? Because if you think about this, k is qx modulo x cube plus 2. So that means image of x here is x bar, but x bar cubed plus 2 goes to 0. This is x bar cubed plus 2. X cubed plus 2 goes to 0, which is x bar cubed plus 2. That means x bar is a root of f, which was the polynomial I started with. It's a root of f. F is x cubed plus 2, so x bar is a root of f. So then we forget all this and think of x bar as alpha, and we say that is a root of f in an extension field k of q. Okay, this is the illustration of the procedure that I described here. So the upshot is, for every irreducible polynomial there is a natural field extension in which the irreducible polynomial we started with has roots. Now this process can be generalized to show that there is always a large enough field where every polynomial has all the roots. More precisely, every polynomial splits completely. So now let me write the proposition that I was writing earlier. The proposition says, let f be a field and let small f be a polynomial over capital F, and I am no longer assuming it's irreducible. Then there exists a field extension k of capital F such that small f splits completely over k. Remember, I defined the notion of splitting completely over an extension field. That means the polynomial splits or is written as a product of linear polynomials. The remark above this proposition showed that for every irreducible polynomial there is an extension field where the irreducible polynomial has a root. Now I am saying that for every polynomial you can construct a large enough field where the polynomial splits completely. The idea is that we are going to induct on the degree of f, small f. Okay, so degree of f is 1 means what? That means f already splits completely. F is already a linear polynomial. That means it splits completely over capital F itself. So take k equal to f. The goal of the proposition is to exhibit a field extension over which f, small f, splits completely. If degree 1, then we can just take it to be the base field itself. Now let's say degree f is at least 2. Now we know, since fx is a UFD, f small f can be factored uniquely as a product of irreducible polynomials, right? This is the consequence of fx being a UFD. So what we can do is let G be a an irreducible factor of f in capital Fx. Let it be an irreducible factor of f in capital Fx. So now by the process described above, there exists a field extension k of f, let's say f1 of f. I want to keep k as the final field I get, so I call this now f1. There exists a field f1, field extension f1 of f, in which g has a root, say alpha. So just to recall, how do we construct such an extension field? We simply take f1 to be fx modulo gx. It's an extension field of f and x bar is a root of g. Because g is a irreducible polynomial, f1 is a field. So alpha is a root of f also. Right? This is clear because f of alpha is g of alpha times h of alpha. Right? G is a factor of f. So that means f is gh. So f alpha is g alpha times h alpha, which is 0 because g alpha is 0. So now we can write, so note that since f alpha is 0, x minus alpha divides, okay, this is something I have done earlier when I talked about rings, ring theory part of the course. If you have f alpha is 0, that means alpha is a root of a polynomial, that means x minus alpha is a factor of fx, because you can always divide by x minus alpha and the remainder is a constant because x minus alpha has degree 1. But when you plug in alpha, f alpha becomes 0, x minus alpha becomes 0, so the remainder is 0. So we can now consider f1 to be fx divided by x minus alpha. This is in fx, f1x rather, because alpha is only in capital F1. Right? This division is not necessarily true in capital Fx, but it is true in capital F1x. So replace f by f1 and small f by small f1. Since degree of small f1 is strictly less than degree of small f, we proceed by induction. Remember, we are inducting on the degree. So that means for any polynomial whose degree is less than degree of f over any field, we can construct a large enough field in which the polynomial splits completely. So we can go from f to f1. Here we have f, here you have f equals x minus alpha times f1, and finally we get from, this is induction step, f1 splits completely. So f1 splits completely in over capital F, capital K rather. This means f splits completely over capital K, right? Because what is f? F is just x minus alpha times f1. So the additional term in f is already linear. So if f1 is a product of linear polynomials over capital K, so is small f. So f is also going to split completely over capital K. So that means we have constructed a larger field over which you have the polynomial splitting completely. Okay, this is a very useful construction for us. This tells us that a given polynomial may not have roots over a base field. Lots of polynomials don't have roots in Q, but you can always construct a bigger field where the polynomial will have roots. Not only will it have roots, but it will split completely as a product of linear polynomials. So now let me define this very important notion, and this is the point of this video. Let capital F be a field and let small f be a polynomial over capital F. A splitting field of small f over capital F. Again, this entire phrase is important for us. A splitting field of small f over capital F is an extension field K of F such that two conditions. F splits completely over the bigger field over capital K. Say F can be written as x minus alpha 1, x minus alpha 2. Remember, splitting completely means it is a product of linear polynomials and they are all in capital K. So it is a product of linear polynomials over capital K, and capital K must be generated by these roots. It should not have any unnecessary elements. Okay, so it is exactly the splitting field. So now the definition is, now the proposition is, every polynomial has a splitting field. Let F be a field and let small f be a polynomial over capital F. Then small f has a splitting field over capital F. What is the proof? By the previous proposition, there exists a field extension K of F over which F splits completely. Right, so this is the first condition for the splitting field. Small f should split completely over the bigger field. But there is also the second condition. So now in the previous proposition we didn't take care of the second condition. Now we are going to do that. So say small f is, it splits completely, right? So we take x minus alpha 1 times x minus alpha 2 times x minus alpha n with alpha I in capital K. It is not true that capital K is the splitting field of small f, because the second condition may not be satisfied. But no problem, it's very simple to get a splitting field. Simply define L to be capital F adjoined alpha 1, alpha 2, alpha n. This is of course in K. So we have constructed a field in the previous proposition K, and F is our base field, and now I am defining a new field only using the required elements alpha 1 through alpha n. So then L is a splitting field of small f over capital F. Right? Now this is clear because F splits over L also, small f splits over L also, because this factorization which was a priori defined over capital Kx also holds in Lx, right? Because what is the meaning of this holding in Lx? All we want is that the coefficients of this polynomial are in L, but L was constructed so that all the alpha i's are in L. So this holds in Lx. That means small f splits over capital L, and by construction the second condition holds. L is equal to f alpha 1 through alpha n. So L is a splitting field of small f over capital F. Let me write another nice proposition before doing some examples. Let capital F be a field and let small f be a polynomial over that field. Let K be a splitting field of small f over capital F. A quick remark here which I will not write and I will not use this much, but splitting field is essentially unique. meaning if you have two splitting fields of the same polynomial over the same base field, you can exhibit an isomorphism of the two splitting fields over the base field. So often when you read books, they talk about the splitting field, and that's a statement which is valid up to isomorphism. But I'm not going to use that a lot, so I'm going to keep calling this a splitting field of small f over capital F. Then K is a finite extension of capital F. So splitting fields are automatically finite extensions. So this is very simple, because by definition K is f alpha 1 alpha 2 alpha n, right? So this sits inside a tower like this. So this is generated by alpha n over this is generated by alpha n minus 1 over this, and all the way up to f alpha 1, let's say alpha 2 alpha 3, to f alpha 1 alpha 2 to f alpha 1 to f. So I have broken up this into a series of field extensions where each one is generated by a single thing. So this is generated by alpha n, this is generated by alpha n minus 1, the next one is generated by alpha n minus 2, this is generated by alpha 3, this is generated by alpha 2, this is generated by alpha 1. But now by what we did in a previous video, if you have an algebraic element and you have an extension generated by this is finite, right? This is finite. Similarly, this is finite, this is finite. Everything in this tower is finite, right? So everything is finite, the entire thing, in other words, because of the multiplicative property of degree of field extensions, K over F, the degree will be product of this times this times this times this times this. So this is finite. So that's the proof, okay? So I have done this pictorially, but I hope it's clear. If you have a splitting field, it's automatically a finite extension. Let me now do a few examples to end the video, and we will continue from the next video. So just I will do 3 examples. What is the splitting field of? So the question is to find splitting fields. So I'll give 3 examples. Find splitting fields. So let's take capital F to be Q and small f. In all examples actually F is Q, so I'll change the polynomial only. So x cubed minus 2. What is the splitting field here? So here K can be taken as Q adjoined cube root of 2 and omega. This is something that came up before. There are 3 roots here. Actually it can be written as, it has to be written as, because these are the 3 roots and this polynomial does split completely over this, right? Because it is x minus cube root of 2 times x minus omega cube root of 2 times x minus omega squared cube root of 2. But it's not necessary to list all 3 elements here, because if cube root of 2 and omega cube root of 2 are there in this field, their ratio is going to be there. That means omega is there. But once omega is there and cube root of 2 is there, omega cube root of 2 is there, omega squared cube root of 2 is there. So this is sort of a minimal generating set. So I can describe this as the splitting field. And what is its degree? So let me not, okay, so I will postpone that degree calculation to later. Let me do one more example. X power 4 minus 1. What is the splitting field? Here what are the roots? Let's say in C. So we have to see, for Q there is a God-given field over which all polynomials have roots. That is related to the fact that C is algebraically closed, which I will formally mention in a later video. So what are the roots in C? They are 1, minus 1, I, minus I. So the splitting field is simply given by Q adjoined 1, minus 1, I, minus I, because you have to add all the roots. But of course it's not necessary to add 1 minus 1, that are already in Q. That is silly to write like that. And in fact, you also don't need to write minus I, because minus I is already there if once I is there. So this is the splitting field. You adjoin one of them, that's enough. In the first example, you have to adjoin two elements to Q to get a splitting field. Here you have to adjoin only one. Final example for this video, x power 4 plus 1. So note that roots here are roots of x power 4 plus 1 are 8th roots of 1. Because remember, if alpha power 4 plus 1 equal to 0, that means alpha power 4 equal to minus 1. That means alpha power 8 is equal to 1. So alpha power 8 is 1, and alpha power, all the roots must satisfy this condition. But some root cannot be a fourth root of unity. There must be a primitive 8th root of unity, which is the root of this. So a root of x power 4 plus 1 is a primitive 8th root of 1. So for example, we can take this to be e power 2 pi I by 8, which is e power pi I by 4, which is cosine pi by 4 plus I sine pi by 4. So this is 1 plus I root 2, right? So this is a root of 1 plus I by root 2 is a root of x power 4 plus 1. What is another root? I is also a root. That is clear, right? Because, sorry, I is not a root. So this is a root. So all the roots are primitive roots of unity. And one of those primitive roots of unity is this, primitive 8th root of unity. Let's call this alpha. Then what is alpha squared? Alpha squared is actually I, because you can check that by multiplying this, because alpha squared is 1 plus I whole squared by 2. This is 1 plus I squared plus 2I by 2. So this will cancel and you get I. Okay. Also it follows from the fact that e power 2 pi I by 8 whole squared is e power 4 pi I by 8, which is e power pi I by 2. So which is I. So alpha squared is in K. Whatever is our potential splitting field contains I, and it contains I plus 1 plus I over root 2. So 1 plus I by root 2 is there, I is in there. That means 1 plus I is also there, right? Because say K certainly contains Q. So we are looking at extensions of Q. 1 is there, I is there, 1 plus I is there. That means the ratio of these two is there. Root 2 is there. So what I want to say is that K is in fact equal to, so certainly these two together imply that K contains Q adjoint I comma root 2, right? But in fact K is equal to Q adjoint, right? That is because 1 plus I by root 2 is already in Q adjoined I comma root 2. This means all 8th roots of unity are in Q adjoined I comma root 2. See, the roots of unity form a cyclic group under multiplication, and a primitive root of unity is a generator of it. So once one of those things generators is there, its powers will be there. That means all other roots are also there. So once all roots are there, all 8th roots of unity are there. That means all roots of x power 4 plus 2 are also in q adjoint I comma root 2. Okay, so that means q adjoint I comma root 2 is a splitting field of x power 4 plus 1 over q. Okay, what I have said here, just to summarize quickly, I am interested in the splitting field of x power 4 plus 1. We first observe that all roots of x power 4 plus 1 are roots of 8th roots of 1, and one of them must be primitive 8th root of 1. So I am taking that to be 1 plus I over root 2. That must be a root, and what I noted is I and root 2 must be in the field, but once you put I and root 2, every other root automatically can be expressed as a rational polynomial in I and root 2. That means it contains all the roots. And if you remove either of I or root 2, you will not get all the roots. So q adjoint I and root 2 is a splitting field of x power 4 plus 1 over q. So our picture is q adjoint I comma root 2 containing qi. Of course, it contains two fields, q root 2 qi, and both are extensions of q. This is the splitting field of x power 4 minus 1. This entire thing is the splitting field of x power 4 plus 1. So let me stop the video here. The last example I went over fast, but please watch the video again if you need to, and ask questions in the discussion forum if you have any doubts. Thank you.